Welcome everyone to this new session of our seminar. So we're very happy to announce that we're currently being funded by FMGH. So yeah, we're getting big, it would seem, in some sense. So we're very happy about that. And we're also very happy to listen today to a presentation by Giuseppe Di Giulio, who's currently a postdoc at the University of Würzburg. I'm not sure about the German pronunciation. And he's going to talk about charge moments and symmetry-resolved entanglement in two-dimensional free conformal field theories. So, Giuseppe, the stage is yours.
Thank you very much for the nice introduction, and thanks to all the organizers for giving the opportunity to speak in this nice series of seminars. Today I'm going to tell you something about a couple of works that I've done in collaboration with Filiberto Ares, Pasquale Calabrese, and Sara Murciano, where all of us were at SISSA, where I did my PhD. And the topic is, broadly speaking, about entanglement in conformal field theories and a symmetry resolution. That is something that recently have been extensively studied. So since about the topic is entanglement, let me start from the very basic. Okay, so let's consider a system of two qubits. One left and one, we call one left and one right, and we say that the Hilbert space of the left qubit is HL and the one of the right is HR. Now let's consider a state in this Hilbert space, and we know that we can construct the projector out of this state, and it gives rise to the density matrix. That is an operator acting on the Hilbert space that describes the state, the quantum state we are considering. Then assume that we can access physically only the left qubit of this system, and then the information about only the left qubit, but taking into account the fact that it is in a quantum system also where also the right qubit is present, is provided by the reduced density matrix. This is obtained from the density matrix rho by performing a partial trace over the Hilbert space HR. And we denote here by the reduced density matrix by rho of L. And now, just to be more concrete, let's consider two examples. So the first one is where the state psi1 that is simply given by a tensor product of two basis vectors in the two Hilbert spaces. And by performing computing the density matrix and then its reduced density matrix for the left qubit, we discover that the expression is this one. It's simply a projector. It means that the left qubit is probability 1 of being positioned towards up, let's say, in this choice of basis. But now we can take another state, another example, psi2, that is different, of course, written in terms of this quantum superposition. And now if we compute the reduced density matrix again of the left spin, we discover that now the situation is different because now we have the qubit or spin. Yes, I'm using interchangeably these two notations. So the qubit can be pointing up or down. In both cases, probability 1/2. So let's say that now we are not sure anymore about the actual configuration of the left spin. And somehow there is a crucial difference between these two states. In the first one, the spin left is we have probability 1 for him to be up, and in the other case we have some uncertainty. And this entirely difference is due to how the qubit left is actually correlated with the qubit right. And this correlation, the property of correlation that is purely a quantum effect in this case is purely due to the fact that both the qubits appear in a quantum state, is a fundamental trait of quantum mechanics and is known as entanglement. And if we want to quantify the entanglement between the left and the right qubit, one can compute the von Neumann entropy of the reduced density matrix and discover that for the first case, we get 0, while for the second example, we get logarithm of 2. That is actually the maximal allowed in this setup. So the von Neumann entropy computed on the reduced density matrix is typically called entanglement entropy, which is a way to quantify the entanglement between a subsystem of a given quantum system. And for this reason, we are going to call states of this type unentangled and state of the type 2 as entangled, actually maximally entangled. Of course, we want to study much more complicated situations, for instance, the one of many-body systems. So imagine to have quantum systems with many particles, many degrees of freedom, for instance, described by a lattice model. Then the idea is that we fix a time slice. Now we fix the time, so the dynamics will not be involved in my talk. And we take a spatial bipartition of the system into a subsystem A and its complement B. So also the Hilbert space can be factorized into HA and HB, and we can repeat the procedure I introduced before and defining the reduced density matrix of the subsystem A. That is, in general, a very complicated operator for a general many-body system that encodes the property of the entanglement between A and B. So we are talking about bipartite entanglement, namely entanglement between a part and its complement. As said before, to quantify this entanglement entropy is a very useful quantity, but as you already see from the definition, we have to compute the logarithm of the reduced density matrix. Being the latter a very complicated object, this task is in general quite difficult. So for this reason, usually it's more convenient to compute the entanglement entropy through the computation of the Riemann entropies that, as you see, involve, from the definition, they involve the trace of rho a to the n, namely the moments of the reduced density matrix, and then after the trace is taken, we take the log. So this computation is much simpler. And why we need it? Because suppose that this expression is known for any value of n, then we can take the limit n going to 1, and we retrieve the entanglement entropy. It's simple to see from this formula. Okay, now let's make another step, and let's assume that our many-body system is critical. As you know, often a criticality, quantum systems can be described by conformal field theories if we take the continuum limit, and their description is given by conformal field theories. And in this case, we are going to focus on two-dimensional CFT, or 1 + 1 dimensional, where fixing a time slice means considering, for instance, the fixed time slice is at the real line if you assume that the CFT is on a plane. And for instance, we can consider the entanglement entropy of a CFT in its ground state, where the subsystem is taken to be an interval of length L, and we compute the entanglement of the interval A with respect to its complement. Now, this is essentially the entanglement entropies of this subsystem in this kind of theory is one of the most important results in the study of entanglement in CFT. It was obtained in these works, and as this is a very interesting expression. So here n is the Riemann index, C is the central charge of the CFT that they are considering. Then this result holds for any two-dimensional conformal theory, so it's very general. And then we have a logarithmic dependence on the subsystem size, and we have epsilon here that denotes the UV cutoff. Essentially, we assume that our CFT has a lattice regularization, so we assume to regularize the CFT with a lattice, or in other words, epsilon is simply the smallest distance that we can access. And you immediately see that if you take the limit epsilon going to 0, we try to remove this UV cutoff, the entanglement turns out to be divergent. So this is a known fact that entanglement in quantum field theories in general is a divergent quantity. But still, as you can see, it's very interesting and insightful to study the scaling of the entanglement, so how it diverges, essentially, its degree of divergence with the cutoff, because, for instance, it can gives us information about the universality class of the system, because, for instance, here appears the central charge of the underlying conformal field theory, and this gives physical information about the system. So this was essentially the first very important result. Then recently people started to study entanglement also in other respects, introducing other ingredients, for instance, global symmetries. So the symmetry resolution of entanglement is a diagnosis of fine structure of the entanglement in case where theories are endowed with a given global symmetry. In this talk, I'm going to focus on the case where the symmetry is given by U1, is a U1 symmetry. That is the first non-trivial example of continuum symmetry. As you know, the symmetry in a quantum system induces the conservation of a charge. We assume this charge Q to be written as QA plus QB, where QA is the contribution of the charge in the subsystem A, and QB is the contribution in the complement. Now, we also assume that the state that we are considering, like for instance, the ground state of the CFT, is in an eigenvector of the charge. Well, if psi is an eigenstate of is actually the vacuum state of the CFT, and the CFT is a global symmetry, this is always true because the state is invariant, and in particular is an eigenvector of the charge. But in general, I mean, we can also generalize this analysis to other states. But let's keep in mind the vacuum state as an example because it's the one that we are going to take for the rest of the talk. As you also know, if we now take the density matrix of this state and we take the commutator with the charge Q, the commutator is 0 because of the conservation. And this commutator stays vanishing if we consider, if we take the partial trace of the relation, and we consider the commutation between the charge QA restricted to the subsystem A and the reduced density matrix that I introduced before. So this vanishing commutator has a consequence that is simply comes from linear algebra, namely the fact that the rho A in some suitable basis can be written in a block diagonal form, where each of the blocks is labeled by one of the eigenvalues of QA. We are going to call in the rest of the talk these eigenvalues charge sectors. And then now, of course, we are very tempted to say, okay, now we have this decomposition of a rho A into various blocks. Can we define a reduced density matrix for each of the blocks, namely for each charge sectors? The answer is yes, but we have to be careful because the reduced density matrix has all the density operators as normalized to 1, as trace equal to 1. While in general, these blocks have a trace different from 1. Therefore, what we can do is to first access each of these blocks by using a projector that we have denoted here by pi a of q. And then we divide the resulting operator by its trace in such a way that the resulting rho a of q has trace equal to 1, and then can be regarded as a full-fledged reduced density matrix, but now associated to the charge sector Q. And therefore, we have that we can write the density matrix as a sum over all the sectors of the reduced density matrices rho A of Q, weighted with this function P of Q that is not called P by chance, but it's called P because this is an interpretation of probability of measuring the charge, small q, if we measure in subsystem A. Just to be more clear, in the entire system, the charge is fixed because the state we assume to be an eigenvector of the charge. But if we now take a subsystem, the charge restricted to the subsystem has a value that can fluctuate between inside and outside. And therefore, this distribution is in general non-trivial and worth to be studied. And once we have the reduced density matrix associated to a subsystem A, we can compute the entanglement associated to each of the charge sectors, introducing the so-called symmetry-resolved entanglement entropy, and is a Riemann generalization in this way. Now, a very interesting fact about the symmetry-resolved entanglement entropy is that if we consider the total entanglement entropy, the one I defined in the previous slides, one can easily show that it can be decomposed as a sum over all the charge sectors labeled by Q of two terms. The first term is basically a weighted sum of entanglement entropies SA of Q in each charge sectors, while the second one, if you can already recognize a von Neumann entropy of a probability distribution P of Q that takes into account, so the first one takes into account the entanglement in each charge sector, and the second one measures the entanglement occurring between different charge sectors. So this decomposition is particularly insightful because it was one of the first thing that was looked at in this context of the symmetry resolution. Particularly, it was measured in some experiments done by Lukin and collaborators. In particular, they were looking at the temporal evolution of the entanglement in a system of interacting bosons in presence of disorder. So this is a system, a very complicated system, but they were able to devise it experimentally, and they made measurements and also numerics to confirm the measure. and they were able to measure the total entanglement entropy, but also the first term of this decomposition that is called configuration entanglement, and the second term that is called number entropy. So what I found, I report here in this plot, is this interesting fact that the configurational entropy reported with the red curve is first constant at the beginning of the time evolution, and then it starts to grow, while the number entropy is initially growing, and then it saturates. And of course, their sum is represented here with this purple line. And so what does it mean? I mean, the outcome of this result, of this experiment, is that the number entropy and the configurational entropy encodes different physical properties, physical features, because they have a different time evolution, for instance, in this case. And since these two quantities can be naturally defined, or actually defined only in presence of, only if we think about symmetry resolution, so only if we perform this decomposition in the charge sectors, studying this property of the entanglement of a quantum system is actually meaningful and interesting to gain more information about the system itself. And then essentially at the same time where this paper was out, also some more theoretical findings was achieved by Sierra and collaborators. And they noticed that for a specific example of conformal field theory, that is the U1 invariant compact boson CFT, that we are going to discuss later on in the talk, the symmetry-resolved entanglement entropy could be computed, and they found that it was independent of the charge sectors at leading order in the EUV cutoff. Essentially, this SA of Q that we are defining at leading order turns out to be independent of the charge sector. And they dubbed this property very naturally equipartition of entanglement. At this point, these two work essentially sparked the interest of an entire community interested in entanglement in many-body system to study the symmetry resolution of entanglement, and many results have been obtained in quantum field theory since then, in various cases like free massive theories, integrable QFTs, also QFTs with non-abelian symmetries, and the case of conformal field theory that is the goal and the main topic of this talk. Okay, so in the rest of the talk, I'm going to discuss the following topics. So I will try to describe how to compute, which are the techniques to compute the entanglement entropies and their symmetry resolution in two-dimensional quantum field theories, with a special focus to CFT. And this will require the introduction of auxiliary quantities known as charge moments, and I will show you a computation of them in the free Dirac CFT. Then I will generalize the charge moments to multi-charge moments, trying to understand why they are physically interesting. And I will provide a couple of examples of computation of these quantities in the context of free Dirac CFT and free compact boson CFT. And in the end, I will draw some conclusions and some future perspectives. So before start, if you have some questions on the introduction, feel free to ask. And also throughout the talk, if you have some doubts, feel free to interrupt me. Okay, so let's start from discussing entanglement in two-dimensional QFT. In this case, it's very useful what I told you before, namely that the entanglement entropy can be seen as the limit n going to 1 of the Riemann entropies. And in order to compute trace row A to the n, that is the key object to achieve the Riemann entropies, a very convenient setup is the one of the replica trick. So we assume that n has integer values, and we try to compute this quantity in that setting, and then we'll try what I want us to do is analytic continuation for real value of n in order to take this limit. But let's go with order. We consider an integer value of n. And what was shown in this work, a seminal work by Calabrese and Cardi, was that one can exploit the path integral representation of the reduced density matrix to write trace row A to the n as a ratio of partition functions, where these partition functions are partition function of the CFT, that one is of the QFT in general, that one is considered. That is defined not on a single plane, but on an n-sheeted Riemann surface that is obtained with the following geometric construction. So one must glue cyclically n copies of the essentially of the two-dimensional space-time, and the gluing occurs along the subregion that defines A. For instance, let me explain this picture. So here we consider the subsystem is a single interval. We denote it by A. And in order to compute trace rho A to the n, using this path-integral representation of rho A, we can imagine to glue together n copies of the same CFT, and the gluing occurs along a cut that is located in correspondence of the interval A that we are considering, that we want to compute the entanglement of. Then, since we have to compute the trace, essentially, we have also to glue. We also have to glue cyclically to close somehow this geometry of sheets to compute actually the trace that it's a cyclic object. Now, essentially, the problem of the entanglement reduces to compute partition function and sheeted Riemann surface that, of course, requires to know the details of the theory and some technology to be developed. But at this point, just to, as I already said, this is very naturally defined when n is integer number, because we have a number of replicas that we want to glue. Of course, we cannot take an irrational number of replicas, but so n must be integer. But once the partition function on this n-sheeted Riemann surface is achieved, then one can try to perform the LIT continuation and take the limit n going to 1. And this, in some cases, possible. In some cases, still not understood how to do it. Because there are, of course, technicalities can arise in that context. This is for generic entanglement, so entanglement entropies. Now we want to make a step further and understand how to compute the symmetry-resolved entanglement. As I told you before, symmetry-resolved entanglement is obtained by studying the reduced density matrix rho A of Q. And from the definition, what one needs actually is to know how the spectrum of rho A is splitted, is resolved in the various charge sectors. So essentially in the block, in the picture of the rho A with the blocks, one should know analytically which of the eigenvalues of rho A falls in each of the block of the total reduced density matrix. And this, from the analytic point of view, is a very difficult and challenging task. So what one can do is to bypass this problem in the following way. So first of all, we introduce this way of writing the resolved Riemann entropies as a ratio of partition functions that now we call charge partition function. Why charged? Because the definition is the same, is trace rho A to the n, but now inside the trace we insert a projection operator that is such that we can select through this projector the block of the reduced density matrix that we want to consider. And now we exploit the Fourier representation of the projector that in the case of that it can easily obtain in the abelian case, and we write the charge partition function as a Fourier transform of another quantity that we call charge moment. There is, again, a trace rho A to the n, but now with the insertion of another operator that now is this flux operator e to the I alpha QA, where QA is the charge, but restricted to the subsystem. This quantity, as was discussed in detail in the work by Seller and Goldstein, can be computed similarly to the one I discussed before as a partition function on the theory defined on the n-sheeted Riemann surface, in this case for the example n equals 3. But now this operator, this exponential operator, is described by the insertion of an Aharonov-Bohm flux. The Aharonov-Bohm flux introduce a phase in so it means that when say some degree of freedom make a closed loop around the entire space, its wave function acquires a phase, and this phase is alpha, where alpha is exactly the parameter that appears in the charge moment. So this is the reason why we insert this Aharonov-Bohm flux. And now, as an example, I want to show like the prototypical example of conformal field theories computation. That is the one for the free Dirac CFT, free massless Dirac CFT. That is very simple CFT, as you know, but still its computation of entanglement in this case has some subtlety, and they essentially arise from the fact, as I already told you, that the geometry where we have to work is not anymore the one of a plane, but now is an intricate and complicated geometry in general. Here in the following, so in the first part of the talk, I'm going to assume that my subregion is one interval. and that the free massless Dirac CFT is in the ground state. So the idea that was developed initially in this work by Casini, Huerta, and collaborators was to the following. So instead of working on a complicated, with a field defined on a very complicated geometry made by n copy of the space-time, it's possible to exchange the perspective and study and introduce a multi-valued fields labeled by psi1, psi2 until psi-n on a single complex plane with a cut that corresponds to the interval we want to compute the entanglement of. We call the endpoints of this interval U and V. And the realization of the replica geometry that I showed you before is given by imposing boundary condition for the fields psi1, psi2, psi j, when they cross this cut, when they cross the interval A. In particular, the condition is, so this condition can be formally implemented by inserting two local operators in correspondence of the branching point of the cut. And these operators are called twist fields, particularly the twist field T of U and the anti-twist T bar of V. What do these twist fields do? Essentially, they implement the boundary condition on the component of the vector psi. For instance, T applied on psi I increase the index I, that is called the replica index, by 1 unity. While the anti-twist that act in the opposite way, when acting on the replica field psi I, decrease the replica index by 1 unity. So actually, it's possible to show that the n-sheeted Riemann surface partition function of this theory can be written as a two-point function of twist fields. Now, in order to understand how to compute this two-point function, the idea is to change the basis for this vector and go in a basis where the twist field acts diagonally. And this can be done, so we introduce a new basis here, in which the components are labeled by psi tilde, and the generic components will be psi tilde k. And this basis is such that when we act with a twist field of one of these components, the only thing that the field happens to the field is that just that it gets multiplied by a phase. And therefore, so namely, going across this cut, as represented here in this picture, the fields pick a phase of e to the 2 pi a, where a is k over n. So essentially, on each, you can imagine that now each of the twist field, so the twist field also can be written in components, like the diagonal basis in the entries of the diagonal. And when these entries act on these fields, they just get a multiplication by a phase. So what does this imply? So we can write the Lagrangian of the theory in the diagonal basis, and it is essentially just a sum over the replicas. But now this implies that the partition function on the n-sheeted Riemann surface factorizes in n terms. Here I've just labeled the components with this parameterization from 1 minus n half to n minus 1 half, just convenient parameterization. But now we have to compute the product of n two-point function of these twist fields defined on each replica. And in order to understand how do they look like in this work by Casini and Huerta, they consider a bosonization. So they mapped the free massless Dirac CFT in its bosonic dual. There is a compact boson CFT. Now, in the bosonic picture, an operator that realizes a multiplication by a phase on the field on the fermionic field is a vertex operator. Vertex operators that are primary operators in the bosonic CFT, whose scaling dimension can be written as, in this case, as k over n squared, namely is the charge associated to the vertex operator to the power 2. Now, vertex operators, as I said, are primary operators, and therefore two-point function of vertex operators are known by conformal invariance. And we can compute them, plug inside the product, and get the expression for the partition function on the n-sheeted Riemann surface. That is, first of all, this Cn is a non-universal constant that we are not taking into consideration because we are interested in the leading behavior of this quantity in the subsystem size. The subsystem size appear here as like the length of the interval, u minus v. And here we have the non-trivial exponent depending on n, and with a prefactor that is 1/6. Let me stress that the one that appear here at the numerator of that fraction is exactly 1 because 1 is the central charge of three massless Dirac field. If one reproduce this computation for general CFT, the formula would be the same, but instead of 1, there would be just C being the central charge. This essentially allows to compute, to obtain the result for the Riemann entropy I showed you in the very first slide. But now we want to understand how this approach, that is called diagonalization in the replica space, change if we want to compute the charge moments now. I remind you the charge moments amount to insert in the end-sheeted Riemann surface a Aharonov-Bohm flux. And indeed, what essentially changes is just that now the boundary condition that the replica fields have by crossing the cut are modified by the presence of the Aharonov-Bohm flux. So the computation goes exactly as the same. I will not repeat it. The only difference is now that twist field implement in the diagonalized basis, let's say, allows the fermionic field to be multiplied by a phase that now does not depend only on the index k, but also on the phase that we have inserted in our end-sheeted Riemann surface, namely on alpha. And therefore, the twist fields are modified because we are slightly changing the boundary condition that they implement. And also the vertex operator will change as a consequence, but we can keep track of this modification. And since we know, again, the scaling dimension of the vertex operator, we can obtain, again, we can compute the partition function, and we obtain this result in the red box. That are the charge moments for generic value of n of the free massless Dirac CFT. Again, this constant is non-universal. Let's focus on the denominator, where you see that this can be rewritten essentially as a Gaussian function of the parameter alpha. And this is the way that we're going to, this is the idea we are going to follow now, because we can rewrite the charge moment in this way, where we have factored out the previous result on the partition function of the end-sheeted Riemann surface times the non-trivial dependence on the flux that is given by a Gaussian function. Here, previously there was a function Cn, a constant Cn in front of it. I have plugged the dependence on Cn in this cutoff epsilon, that again in general is a non-universal constant, that in general depends on n and alpha. Since we want to describe only the leading behavior in the cutoff, we can drop the dependence on n and alpha, and to compute the charge partition functions that are useful for the symmetry-resolved entanglement entropy, we have to perform the Fourier transform of this Gaussian. That can be easily seen to be another Gaussian. Here we are taking the saddle point approximation under the assumption that, let's say, the ratio between u minus v, so the length of the interval, and the cutoff epsilon is very large. And now that we have this charge partition function, we can just take the ratio and compute the symmetry-resolved Riemann entropies that have this expression, where here I have reported only the leading term in the expansion epsilon going to 0. This order 1 means that terms are only all of them are subleading in the regime epsilon going to 0. Let me quickly comment this result. Here we have that the symmetry-resolved Riemann entropy is equal to the total entanglement, the total Riemann entropy minus a term that is a double logarithm in the subsystem sides and in the UV cutoff. Now, this double logarithmic correction is a feature of the symmetry resolution. Usually, you don't have in the computation of the entanglement, and is a peculiar feature that even if differs, of course, from the total entanglement, you see is independent on the parameter Q that we have here. Namely, is independent on the charge of the charge sector that we are probing. And indeed, the fact that the leading order is independent of the charge is exactly the equipartition of entanglement that I was mentioned previously, first found by Sierra and collaborators. Actually, these higher order terms in general will depend on Q. And typically, it's very interesting to go and investigate case by case how this breaking of equipartition that is non-universal, therefore depends really specifically on the model, occur. And actually, for this example of CFT was shown in these works that occurs at order 1 over the logarithm of the subsystem size to the power 2. So it's really subleading because we are taking the limit of the length very large, L going to infinity. Okay, so this was the first example I provided you. Now we have understood that symmetry, so resolved entanglement can be computed with the charge moments. I've shown you how to do it for the case where this subsystem is given by a single interval. Now let's take a more difficult case, namely the case where the interval is given by two disjoint intervals, A1 and A2. In this case, one can define like a generalized version of the charge moments that are called the multi-charge moments. Here, essentially, the idea is simply to take the charge associated to the subsystem A, to split it in the two contributions associated to A1 and A2, and then to associate to each of them a different phase. In this case, just A alpha and beta. And therefore, with the same logic as before, these multi-charge moments can be computed as a partition function on an n-sheeted Riemann surface, where n is this index here. But now, the Aharonov-Bohm fluxes that we introduce will not be simply one, but there will be two. One of them, each of them piercing the two intervals that determine our subsystem A. So why this quantity, why multi-charge moments can be useful? Of course, if we want to study the symmetry-resolved entanglement entropy, it's enough to take alpha equal to beta and apply the procedure I showed you before. But there is a recent development that one can, let's say, access through this new definition. So to go there, let me consider the Fourier transform of the multi-charge moment with n equal 1. That can be checked to have the meaning, physical meaning, of a joint probability of measuring the charge Q1 in the subsystem A1 and the charge Q2 in the subsystem A2. Now we have a joint probability. We can apply the Bayes theorem by dividing it by the probability of having the charge, the total charge in A1 union A2 equal to Q. And what we get is the conditional probability of measuring charge Q1 in the subsystem A1 under the condition that the total charge in A is equal to Q. This conditional probability turns out to be useful to define the symmetry resolution of another correlation measures in quantum systems. That is the mutual information. The mutual information is a measure of correlation between two parties of a given quantum systems. For instance, in this case, we can imagine that we want to compute the correlation between A1 and A2, because I remind you that the entanglement entropy measures the correlation between the union of A1, A2, and their complement. But it doesn't tell anything about the mutual correlation between A1 and A2. This is an information that actually is encoded in the mutual information that is defined in terms of the entanglement entropies of A1, A2, and their union in this way. Now, in this work by Calabrese and collaborators, it was pointed out that it's possible to write a symmetry resolution also for the mutual information that have this expression where the symmetry resolved mutual information I of Q can be written now in this way and can be computed from the knowledge of the symmetry resolved entanglement entropies of A1, A2, and the complement. You see that in this definition, there is the conditional probability introduced before popping out. And so if one wants to know the resolution of the mutual information, one must first consider compute the conditional probability I told you about. So in the rest of the talk, we are going to focus only on the charge moments in two cases of CFT, but then, of course, one from them can compute also the mutual information, but that, let's say, goes beyond, because in the end, it's just a bunch of algebraic computation, where to compute the multi-charge moments, we have to use CFT techniques. That is the main focus of the talk. So one free result, almost free, is repeating the computation in the free Dirac CFT. Now, the bipartition geometry is given by this diagram. We have the two intervals with length L1, L2 respectively. We assume they are separated by a distance d, and we call the four endpoints, two for each interval, as U1, V1, and U2 and V2. Now we can actually repeat, exploit the diagonalization in the replica space that I explained you in the previous slides, and everything goes exactly as before, in the sense that the multi-charge moments on the n-sheeted Riemann surface can now be computed as a product of n correlation function of vertex operators, where now we have to take into account 4-point partition 4-point correlation function. Why 4 points? Because we said that we insert operators at the endpoint of our subsystem, and in this case, a subsystem have 4 endpoints. Therefore, we need to insert 4 vertex operators. This product of correlation functions can be computed, and the result turns out to be the following. So we have that the first part is actually exactly equal to the n-sheeted Riemann surface partition function, and then we have the non-trivial dependence of the flux that is contained in this second factor. And this is despite, I mean, it's in general, in this case, it's very simple, relatively simple, just given by algebraic functions of the length of the intervals and their separation that comes in this formula through the parameter x, where the parameter x, yes, is the cross ratio that is typically pops out when we compute a 4-point function in conformal field theories. So also in this case, it makes the formula much simpler, and is defined in terms of the parameters L1, L2, and D in this way. Now we want to go to a different case where the diagonalization in the replica space cannot be applied. So we change model. We take another CFT where we cannot apply this method, and we see how the computation must change. The CFT I'm talking about is the compact boson CFT that, as you probably know, is described by an action of this form, where the scalar field phi now has a compact target space. Namely, there is the identification between phi and itself plus 2 pi r times m, where m is an integer number and r is a positive parameter we call compactification radius. Actually, I mean, it's not necessarily positive, but it's real. So this model has also U1 symmetry. I didn't mention explicitly, but before we consider free massless Dirac theory, we know that that is a U1 symmetry where the conserved charge is the number of particles. Actually, number of particles minus number of antiparticles. That is the charge that we were looking at in that case. Here, the U1 symmetry is generated by this charge. That is simply the integral of the derivative of phi. That, differently from the one of the free Dirac case that I discussed before, is a charge that is conserved just by Bianchi identity, and not really because of the Nether theorem. But apart from this, well, we are going to see how we can perform the symmetry resolution with respect to the charge sectors induced by this U1 symmetry. But before that, let me just give an overview on the null result for the entanglement of this theory if the subsystem is given by 2 intervals. Okay, again, we take the same geometry as before, but now we will see that with this theory, the expressions are much more complicated. And I think that in the rest of the talk, the reason why they are so complicated will become more and more evident. So the n-sheeted Riemann surface partition function was computed in this work by Calabrese, Cardi, and Tonni. And the expression is turns out to be this one, where again we have the first part that is is actually the same, the first factor of the free Dirac case. But then we have an additional function of the cross ratio f of n that is given in terms, that is written in terms of these theta special functions that I'm going to describe in a moment. And where here I introduced this parameterization for the compactification radius that is known as a Latinger parameter. These special functions that are denoted by theta are Riemann-Siegel theta function that are a bit cumbersome special functions in the sense that they get as an input n-1 components complex vector and an n-1 times n-1 matrix. Now, the matrix that we have to give as an input of the Riemann-Siegel theta function for computing our goal is a matrix gamma that is a function of the cross ratio only, because that is actually the only meaningful parameter that we have, but is written through a complicated sum of ratio of hypergeometric functions. So it's a very complicated function, but I wanted to introduce here because this will come back at a certain point in the talk. So for the moment, it's just a very complicated result. The later it will get some meaning. I want to stress that here, the dependence on n that I was describing, this is the Renyi index of the Renyi entropy, comes in, for instance, in the sides of this matrix, because this matrix is n-1 times n-1. Therefore, you understand that it's very difficult to perform the analytic continuation in a straightforward way, because it does not make sense to have a matrix with complex sides. And therefore, in order to make the analytic continuation here, there is much more work to do. Actually, this analytic continuation for generic complex value of n is unknown for generic values of k, but is known only for very special cases. But still, despite this, we can still compute the multi-charge moments, or at least see how the n-shaded Riemann surface partition function get modified by the introduction of the flux, by the fact that we are considering multi-charge moments. And as I told you, we cannot rely on the diagonalization in the replica space. The reason is the following. As I will clarify in a moment, if we take our subsystem to be made by two intervals, and we construct the replica space, the resulting manifold, the n-shaded Riemann surface, will have a non-trivial topology. Particularly, we'll have genus higher than 0. And this means that, as you know from topology, we have a large number of non-contractible loops. Now, these non-contractible circles makes impossible to factorize essentially the action of the compact scalar, because now, as you have seen, the compact scalar has this compactification condition. Namely, we are identifying the fields. For instance, every time that the fields goes across closed loop, it will pick up, let's say, just an additional contribution given by 2 pi r times some complex, some integer numbers. But since now we have many contractible, non-contractible inequivalent loops, this compactification condition cannot be factorized, and therefore we cannot write the theory as a product of theory or sum of theories on different phases, on different replica sheets, replica spaces. So this allows us to think about a different strategy, and what we resort is the following idea. We write the operator that we have to insert in the trace to compute the multi-charge moment as, I mean, from the definition of the charge for the compact boson, you can immediately see that with simple step, this operator can be written as the product of vertex operators. Let me stress that these vertex operators that now must be inserted correspondence of the endpoints of the n-sheeted Riemann surface, here represented as a 3-sheeted Riemann surface, are slightly different, but fundamentally different from the ones I introduced you before in the dealing with the Dirac CFT. In that case, if you remember, we had the vertex operator on each copy of in each replica of the system. Here, these vertex operators are inserted only in one of the sheets. And therefore, they have a different meaning. So these ones realize the entire Aharonov-Bohm phase, while the other one was just a contribution replica by replica. In the case of compact boson, actually, the vertex operators are still primary fields, but they get a different scaling dimension that now depends on the compactification on the Lattinger parameter, or we have just rescaled in this parameter eta. And then, as I anticipated, and also as you can imagine now, by following this work by Sela and Goldstein, and also essentially what we have discussed so far, what we have to do is to consider the insertion of vertex operators located at the 4 endpoints of the system, but now their correlation function must be computed on a much more complicated geometry. that is the one of the n-sheeted Riemann surface. Then the result must be multiplied by the partition function of the theory on the n-sheeted Riemann surface, but that is, I showed you in the previous slides, now from the work by Calabrese, Cardi, and Tonni. Therefore, this is a known input, and the non-trivial task is to compute this 4-point function. Is non-trivial in the sense that now we have to compute correlation function of vertex operator on higher genus Riemann surface. In particular, if we take the n-sheeted Riemann surface that we denoted here by sigma n, its genus will be given by n-1. And okay, at this point, let's consider one example of this computation to see which is the result. But before this, let me just give another step of the computation. This is a very customary computation in 4-point functions in CFTs. What we can do by a standard conformal transformation is to map the 4 points where we have inserted operators into 4 standard choices that are 0, the cross ratio x, 1, and infinity. So in the rest of the computation that I will sketch, we will keep these 4 endpoints. So the operators inserted in these 4 standard points, and only at the end of the computation we are going to restore the dependence of the multi-charge moments on L1, L2, and the separation of the 2 intervals. So just to start with an example that is a bit easier to understand, let me stress that when n is equal to 2, the 2-sheeted Riemann surface has genus 1. That is the same genus as a torus. So the trick to compute the case n equal to 1 is to map this n-sheeted Riemann surface into a complex torus with a period with periods 1 and tau that will be related to the cross ratio, to the geometry of the n-sheeted Riemann surface in a suitable way that I'm going to show you. So essentially, in the new space, in the new manifold that now is parameterized by a complex coordinate w, the only non-trivial part of the theory takes place on this rectangle with sides tau along the imaginary direction and 1 along the real direction, and this rectangle then gets repeated periodically with period 1 along the real line and with period tau along the imaginary axis. This mapping to the torus actually can be made precise by exploiting the Abel-Jacobi map. That is the function that in general maps n-sheeted Riemann surface into a n-1 complex torus. In this case, we have just the torus, and indeed we map the coordinate z that parameterizes the 2-sheeted Riemann surface sigma 2 into the w that parameterizes the torus. Here, this integrand, okay, is a non-trivial function with some branch cut. Then we have this prefactor that is an hypergeometric function. Let me just summarize everything for convenience of notation inside this function nu. Now, the first thing that we may ask, okay, what happens to the 4 points 0, x, 1, and infinity when we apply the Abel-Jacobi map? Here I represented them in this diagram with different colors. And these are mapped to the specific points of the torus. And therefore, now we know how in this new geometry, the vertex operators are inserted, right? Because in each of these colored points, I remind you, in the previous geometry, we had an operator insertion of a vertex operator. Also, the value of the period tau can be related to the parameters of the sigma 2 surface through the Abel-Jacobi map. And it turns out to be given by this ratio of hypergeometric functions. So now we have all the ingredients to compute the 4-point function of vertex operators in this new geometry, parameterized by W. Now, the 4-point function of vertex operators on a torus, you can find, for instance, in the book by Di Francisco, and is given by this expression that now I'm going to comment. Here, just for convenience of notation, I've called the 4-point 0, x, 1, and infinity, z1, z2, z3, and z4 for convenience. And also the fluxes of alpha and minus alpha have been called here alpha 1 and alpha 2, and beta and minus beta, alpha 3 and alpha 4. Now, this expression looks actually complicated, it's true, but we have all the ingredients to work out some simplification, because this W are essentially the points where the insertion points are mapped that we have computed above. Also in this function in the second product that is known as prime form and is generally defined for any initiated Riemann surface. All the parameters inside this elliptic theta function of type 1 are known. And actually, with a bit of effort of algebra and exploiting all these identities between elliptic theta function, one can write this complicated product in a much simpler form that is essentially concern the second factor only. And then, okay, we compute this, we restore the dependence on L1, L2, and the separation of the interval, and we write down the multi-charge moments in their final form for the case where n is equal to 2. This result, again, is given by the first part, that is the partition function on the torus of the compact of the compact boson, and then we have the second part that is essentially this ugly, is how we have been able to write this ugly formula that I wrote in the previous slides, because it turns out remarkably that this intricate dependence on hypergeometric functions and elliptic theta function can be rewritten as a simple algebraic function of the cross ratio only. And therefore, when we restore the dependence on L1 and L2, the dependence on the fluxes take this very nice form. Therefore, it's reasonable to ask whether we find such a nice result also in the case of IRN. And I'm going really to give the steps that one has to do. I'm not showing you any ugly formula for the rest, and then we will comment the result. But so essentially, the difficulties in considering the IRN case is that now our sigma n, the n-sheeted Riemann surface, has the genus n-1 and two n-1 non-contractible closed curves. Now, the problem of these closed curves, that is also essentially the reason why we have not been able to apply the diagonalization in the replica space, because the partition function of the compact boson does not factorize this replica, is that the closed loop, the non-contractible closed loop, connect different replicas through the cuts. You see here in this example, this is a three-sheeted Riemann surface just for reference. And I've drawn for you the four non-contractible loops that we have in this case, in black and in green. And you see that some of these non-contractible loops connect different replicas. Therefore, really, the idea of writing everything as a product of partition function in each of the individual replicas cannot work in this case, because our field, our scalar field that is defined on the entire manifold, gets a non-trivial contribution if we go across all these non-contractible loops. And now, of course, again, we can exploit the Abel-Jacobi map. But now, as I anticipated before, we map the n-sheeted Riemann surface into an n-1 complex torus. Like, just which are the features of the Abel-Jacobi map? I don't want to show you again, I tell you. But beforehand, we just had this, we were mapping the complex coordinate z of the n-sheeted Riemann surface to another complex coordinate of the parametrizing the torus. Now we are going to map the z coordinate that parameterizes the n-sheeted Riemann surface into n complex coordinates that now parameterize the n-1 torus. I've denoted it like in this way. Then there is another ingredient that must be modified with respect to before. Beforehand, we had, as we discussed, two inequivalent loops. One of them, the period of one of them could be set equal to 1, while the other one has non-trivial parameter that was tau. But now, since we have a higher number of non-contractible closed curves, the periods that are associated to our manifold, our torus, are now not anymore only one. It's not anymore only one, but we have many of them that are encoded in this higher dimensional object that is, in this case, is n-1 times n-1, and is called matrix of periods. Now, I've not chosen the notation gamma here by chance, but this is exactly the same gamma that appeared some slides ago in the definition of the function Fn. So in this sense, also the partition function of the compact boson CFT on this on the n-sheeted Riemann surface knew, of course, about this complicated geometric structure, but in a very obscure way, actually, because this matrix occur inside the Riemann-Siegel theta function. But that was the more formal reason why these matrix occur in the partition function. So that is, if you want, the meaning of this matrix. And finally, okay, once we apply the Abel-Jacobi map, we have we must compute the correlation function. This is known from the work by Berlinde brothers. And okay, one can write down the expression. The problem is now the generalization of the prime form in terms of on the n-sheeted Riemann surface depends in a very non-trivial way on Riemann-Siegel theta function. So in general, how to write this in terms of simple functions of the cross ratio only is not known. So what we have done in the paper that I'm presenting, essentially, we have devised some conjecture for these expressions of Riemann-Siegel theta functions, essentially of prime forms in terms of algebraic function of the cross ratio, and we have checked them numerically for many value of n. So of course it is not a proof, but it's just let's say an argument. So it would be actually very interesting to show them by using properties of the Riemann-Siegel theta function. So after one applies these conjectures, can apply the conformal mapping back to have the dependence on the length of the intervals and their separation, and the results for the multi-charge moments with index n gets this expression that is, despite the high level of complication of the results, is remarkably simple. The first part is again the partition function of the n-sheeted Riemann surface, and all the dependence on the fluxes that we have inserted is given by this amazingly simple algebraic function of L1, L2, and x. So the dependence is exactly the same as the case n equal 2, where the only dependence on n is actually here, and then if you take n equal 2, you get exactly the result that I showed you in the previous slides. So why this is good from the physical point of view? Because now we can easily take the Fourier transform of this object and, for instance, compute the symmetry-resolved mutual information that I showed you before. This we have done in the work, but I'm just not putting here for the sake of time. But from the CFT point of view, I would say that this is a very nice result because we really find a very compact formula and expression for an object that requires a lot of computation, exploiting the properties of this topological and non-trivial n-sheeted Riemann surface. Now, I think I'm a bit out of time, actually, but I quickly summarize. So I've given an overview of techniques to compute symmetries of the entanglement by exploiting the charge moments, that is partition function in presence of Aron-Bohm fluxes. Then we have generalized this quantity to multi-charge moments that turns out to be important for computing, for instance, resolution of the mutual information. And then we have computed these multi-charge moments in 2 examples of CFT that are important. The only outlook that I would like to mention is that despite the computations are non-trivial, these 2 CFTs are free CFTs. Of course, it will be very interesting to understand how this result gets modification in the case of interacting CFTs. And a very promising approach along this line is exploiting ADS-CFT correspondence, that for those of you that know, is a way to compute conformal field theories results in strongly interacting conformal field theories by using general relativity and general gravity results. And so this could be like a setup where extending these results to interacting CFT might be promising and doable. So with this, I thank you for the attention. I'm looking forward to your questions.
Thank you very much. Are there any questions from the audience?
Can you hear me?
Yeah.
Yeah.
Hi, thank you for the very nice talk. So just like a very stupid question. So like in the case of the compact boson, I mean, in principle, you also have another U1 symmetry, right?
Yes.
So what happened when you also, I mean, so far you have been discussing just one of them, right?
Yes, exactly.
And this is the type of resolution that you are explaining. But what happens, I mean, so the result that you are getting, for example, is not invariant under T-duality, I guess.
Okay. So first of all, thank you very much for the question. So wait, let me go back.
I mean, I'm not sure whether it makes sense. I'm just wondering.
No. I mean,
so
it makes
it's just,
absolutely sense. Yes.
So in a sense, there should be a resolution that includes both U1 symmetries, so that you also, in a sense, you have a perfectly a result that is invariant under duality, basically, because they should be treated in exactly on the same footing, I guess.
Okay. So yes. The short answer to your question is yes. The result is invariant under T-duality, but is highly non-trivial to see it. I mean, in the sense that here I'm hiding in the end the dependence on Q in this case. So just let me try how to can I say it in a finite amount of time. So a first suggestion of the fact that the results in the end turns out to be the same is the following. You can write this charge as J0 plus J0 bar. I mean, the argument of the integral, where J0 and J0 bar are the generator, are the zero mode of the current algebra. The other charge will be J0 minus J0 bar. So what changes is just the relative sign between the J0 and J0 bar. Now, actually, when you write in the expression of the charge moments that I give you above, yes, exactly. So here you see that in the end, you get a product of vertex operators. Here I was skipping, of course, the details, but in general, here we have to do this computation, taking the holomorphic sector on one hand and the holomorphic sector on the other hand, and then you take the product. Okay, I mean, I skipped this detail because it was a technical, but now it's important. Because the result that you get for the holomorphic sector is the same as the anti-holomorphic sector. And now, since the two charges you are mentioning change only for the sign between J0 and J0 bar, the two holomorphic and anti-holomorphic components turns out to be the same in the two cases. Therefore, when you take the product, it's also the same, and the resolution with respect to the two charges is actually the same. But I agree, I completely agree that this is not super evident from the...
No, but it's magic. I mean, that's
Yes.
that's great. I mean, absolutely. Thank you.
Actually, there is just to conclude on that point. In the end, both the quantities are, both the symmetries are labeled by let's say integer numbers. What changes? I mean, it's true that the charges are a bit different, but just because they are multiplied differently, like they are scaled differently by the compactification radius, the two charges.
Mm-hmm.
But this in the end, this dependence of the compactification radius gets actually, I mean, yes, it's taken into account by this factor k, because for the other symmetry there is this k is not there because the vertex operators are different, but there is another k arising that cancel exactly this dependence. I mean, there is a mechanism of this type to be even more precise.
So you're saying at the end of the day, the Luttinger parameter is it invariant under T-duality or something like this?
Exactly.
Okay,
yes.
Okay. And I have another question, but this is more like really, well, thanks a lot, first of all. But so if you want to generalize this result to interacting CFTs, like, can you not just in quotes, of course, can you not just include the background charge and simply exploiting the formalism, the Coulomb gas formalism? So you work on the compact boson CFT, but then you add like a background charge at infinity that shifts the dimension of the vertex operators, and also, you know, the neutrality condition. So everything becomes much more complicated. But after all, you should be able to mimic at least the minimal models.
Yes. I think that this is it's a very good point. I'm not aware of anyone that has made some investigation like this, but that would be definitely worth to at least to try. Yes.
It may be extremely complicated, of course.
Yes.
But in principle, the background charge is just, you know, I'm sure you know more than me about it, but so it's just going to shift you know, the neutrality conditions such that at the end of the day you have these weird monodromies to pick up the right, so you have to pick up so the physical 4-point function of vertex operator is given by a certain precise combination of 4-point functions with different vertex operators. I mean, it's I guess.
Yeah, no, I think that it should work. The problem, as you pointed out, should be, I mean, might be the
extremely impossible.
the implementation, but it's a very nice suggestion. Yeah.
Okay.
Thanks.
Well, thanks for the very nice talk.
So are there any more questions that people want to ask to Giuseppe? It seems not. So in that case, thank you again for a very nice and pedagogical talk. Let's clap.
Thank you very much for the invitations.
Wait, Giuseppe, I have another question. I'm sorry. Just something very basics.
Yes.
But so you may have received this question too many times, so I already apologize. Like when you have so can you really factorize the space in say A and its complement when you actually have Wilson lines connecting the two regions?
I think that the reason, so let me do one step back. In general, we could not factorize the Hilbert space. I mean, let me quickly share. Sorry for unsharing. So the very basic assumption that I do when I want to work in this setting, that I claim to work in quantum field theory, that some people would be terrified by this, is this one. Strictly speaking, it doesn't hold for quantum field theories. Because, and this is exactly the reason why the entanglement is divergent. Because this factorization of the Hilbert space is not well defined in QFT. The idea, the rough idea, very rough, is that at each point you have infinite energy density and infinitely many degrees of freedom. Therefore, does not make sense in this way to say where the Hilbert space can be broken into two parts containing degrees of freedom in the space. There are ways to treat entanglement formally, like context of algebraic quantum field theory, when you, instead of talking about Hilbert space, you talk about algebras, but still in that case, the result is that the entanglement entropy is not well defined in strict quantum field theory. So we always have to take in mind that you are going to work in presence of a cutoff. So in presence of yeah, essentially, yes, exactly. In presence of a cutoff, there is a minimal length scale that you can access. Mm-hmm. And in this case, I think that.
But do you think that if you have a Wilson lines, still their contribution will appear in this coefficient somehow, the coefficient of the universal part of this divergence, or not?
Yes, actually.
So like if you take, let's say that you take, I don't know, a gauge theory, for example, just something, you know, with, but you can also just take, I don't know, a minimal model with, you know, where you have line operators, like Verlinde lines, for example. Like, so you consider these, and then you consider a version of the same theory, but in a sense where you formally remove these lines. I don't know if this is possible at all. Will you find the same entropy or not?
I think it is related to the problem of having like entanglement in gauge theories in general.
Yeah, but it can also not be just it can just be like the easing model, you know, with the Verlinde lines. I mean,
yeah, but so I agree with you that the problem, I mean, what here can be done because the vertex, essentially the vertex operator that we that we insert here is actually only in the subsystem A, because this QA is localized in A. I think that I agree with you that if we take a Wilson line that goes across the surface, we cannot really take this factorization. I mean, this at least is my understanding. Because yes, I mean, this is what happens in gauge theory, right? You have the ambiguity, and the problem is that there is ambiguity in computing the entanglement entropy, that some computation in lattice gauge theory show that apparently there is a dependence on the gauge choice of the entanglement entropy. And therefore, essentially, you have to choose if you want to include or you don't want to include the Wilson line. And then if you include, you can still do the factorization, but then you are taking essentially the Hilbert space of your subregion and the Wilson line. If you don't include it, you are pretending that it's not there. So I think that the answer to your question is then yes, the entanglement entropy would depend on whether you include or not the Wilson line, or in other words, it depends on the gauge that you choose for computing it.
Thank you so much, Giuseppe.
You're welcome. Thanks for the nice questions.
Okay, so let's thank Giuseppe once more.
Thank you very much.
And well, I guess if Edo has still a few questions, he can ask you in the future.
Yeah.
And yeah, we'll see you in 2 weeks for the next session of the seminar. And until then, have a nice day. Bye.
Thanks. Thank you very much. Bye.
Have a good day. Thank you.